Hi, I'm Ted Hahn. I'm a site reliability engineer. I work on planet scale distributed systems. I have previously worked at Facebook and Google. More recently, I have been helping small startups do DevOps the right way.
Hi, I'm Mark Hahn, and I'm Director of Cloud Strategies and DevOps for Cyber Global. That means I'm responsible for all things related to software velocity for my company. We're a nationwide consulting company, and we do lots of projects for clients developing various cloud-based systems. So we're going to talk today about a father-son project that we've been working on called Achieving Mutual TLS. And we'll show you what we've done with that in Kubernetes.
So our subtitle on this talk is Secure Pod-to-Pod Communication Without the Hassle. And our thesis is that every Kubernetes pod should include an SSL certificate that verifies its identity. This certificate should be signed by the Kubernetes master and be specific to each pod. Your core infrastructure should include an opinionated web server that has your middleware for logging, metrics, security, all of that. That every software project you start should start from a base that is common across all of your code. This is part of that. This is a Kubernetes controller that you assume is in your environment and that creates certificates for each pod as you, at runtime, as you need them.
Right, so certificates. So I think we know a lot about certificates that we use for TLS, but this is the basic life cycle of a certificate. So you create a private and public key pair, and you take the public key and you turn that into a certificate. You put that in a certificate signing request, and then you pass that CSR off to a certificate authority, and they sign that certificate by using their private key, and that gives a public signature, a public hash. That's bundled together, and that becomes the certificate, which is passed back to the originator. Now that public, that certificate contains public information and can be used for secure communication. And any client without prior knowledge of the server that it's talking to that has a certificate can still have secure communication because they mutually trust the same certificate authority. So a developer can include certificates, and we'll talk about how they get set up for different development environments and how they get included in your code to do TLS.
So this here is an example of how you would manually create these certificates using Cloudflare's CFSSL. CFSSL is a utility that allows you to run a certificate authority. It can run as a web server, or it can simply run as here, just on your machine. In this case, we're showing how to generate server and client certificates locally. Theoretically, these would be three separate roles. That the certificate authority receives requests from both the server and the client independently, and they get back requests. But even here in this simplified example, there's a lot of moving parts. There are three different sets of key and certificate that all have to be managed, and it's very easy to confuse them. It's very easy to simply get them wrong. And the tooling is kind of a pain. The tooling does not give you the right kinds of error messages for it to be very convenient for people to figure it out, because the same thing, a incomplete root of chain of trust is the same as no chain of trust. Exactly.
So CFSSL simplified that. Prior to that, and if you look for these things on the web, you'll find OpenSSL is the tool of choice. It's even more complicated than CFSSL. This is the steps that you would take to develop a certificate authority and to sign key requests, certificate signing requests, and generate certificates in your own environment. OpenSSL is pretty difficult to automate. It was originally built as an interactive tool, and so the automation bits of it are kind of clunky. It's also configured through Windows-style INI files, which are just painful to deal with these days, and you can't pass them around and deal with them too automated. So this tooling is difficult to deal with at best, and then the error messages that you get out of it are kind of cryptic. Other methods for generating certificates is possibly to go purchase or get your certificates from an internet service provider. So you could go to 2Cows or DigiCert and pay for certificates, or you can go to Let's Encrypt, and they've got good automated tooling with the Atom protocol, but those are really designed for public-facing internets. They're not designed for internal usage for your dev, test, and stage environments like you might want to use. If you're going to do that, you might end up using, say, a tool like Microsoft Certificate Authority, which is kind of a bolt-on to Active Directory, or maybe Oracle's Identity Manager or something of that nature. But those big enterprisey tools tend to be big and bulky and again, kind of difficult to manage. They take up a lot of resources. So, and they're not convenient to use when you've got a development team that wants to move rapidly and create and destroy certificates quickly.
So we'll talk a little bit now about how your developers use certificates in their program. We'll show some examples of applications in Golang and Java that make use of these TLS certificates.
Exactly. So, and as Ted said, these are TLS certificates. So hopefully we will stop mentioning SSL for the rest of this presentation. If we do say the phrase SSL, you guys can call us out on that. But from here on forward, we're dealing with TLS certificates, which is the correct name going forward. Cool. So let's see an example in Golang.
Yeah. So this is a simple Golang web server application. It's got a flag that defines its listen port. It starts up, it parses, it creates some backend service, and then registers that backend service's handler functions with the Golang HTTP web framework. Then it calls http.listen and serve, which will theoretically never return. That starts up your web server. So this is the diff for how you change it for using TLS. You specify in additional flags the location of your certificate and your key files, and then down at the bottom, rather than calling listen and serve, you just call listen and serve TLS, and you pass in those key files. Drop dead simple.
If you've got the certificates here, if you've been able to get your certificate authority to give you server certificates and quickly with the server name that you're using, this stuff can be quite simple. Here's an example, a typical example in Java. So in Java, you're probably going to use Spring Boot, and Spring Boot startup is pretty easy. You call Spring application.run on your Spring application, and then that defers to some dependency injected endpoints, REST controller with REST mapping. So this is all pretty straightforward. Lots of microservices developers write this code, multiple times per week. To use TLS with this, it's as simple as adding in the properties that say, I want to use TLS. Here is where my certificate and its private key are stored, and then here's the password that I use to get that certificate, that private key out of the key store. So Java was built with this model that the certificates are encrypted on disk in a file using PKCS12 formats. So you've got to specify this to get up and running. It's difficult to get these things created with the Java key tool. So all of that is machinations you've got to deal with that as a programmer kind of hold you back from actually getting to writing your endpoints here.
So far, configuring your certificates once you have them is easy, but getting the certificate is the hard part. Generating those certificates is fiddly. Storing them securely is fiddly. Error reporting for the certificate tools when you're trying to connect two things that don't have matching certificates just looks exactly like any other error. It doesn't tell you what you're doing wrong.
So the question is, how can we make this easier? Well, I think the answer to that is pretty straightforward.
Yeah, Kubernetes to the rescue. Kubernetes has a certificate authority built in. In fact, you can make the case that the Kubernetes cluster is defined by its certificate authority. And Kubernetes should just create TLS certificates for each pod and service as you need it.
Right. So our project is called KubeTLS, and it adds this layer into your Kubernetes clusters. And it's very similar to what Borg does. Google has a paper on this called ATLS, which spreads certificate around through all of the services that they write. ATLS stands for ALTS, sorry, stands for Application Layer Transport Security, which is giving certificates to every functioning piece of your infrastructure so that it can communicate securely with the other pieces of the infrastructure that it needs. So let's talk about how we did this.
Yeah. So we're going to create a TLS cert that's compatible with the way you use Kubernetes services already. We're going to generate a certificate in every and private key, a private key and certificate for each endpoint, each service endpoint. And then we're going to provide that certificate and private key to every pod that matches that service. All of this is automatically generated by the Kubernetes Central Certificate Authority and trusted by everything else within your cluster.
This is already what Kubernetes does, straightforward. Kubelets join the cluster by creating their own private key, getting it signed by the master, and then all control plane communication happens over these TLS encrypted links using these certificates that are automatically generated by the authority. So when you're building a Kubernetes cluster the hard way, 90% of that work, a whole bunch of that work, is related to just getting those certificates set up and distributed to the right pieces of the cluster so your master nodes can come up. Once you've done that, then your kubelets come up pretty easily because there's already a mechanism to generate these certificates for those control plane endpoints. And all we want to do is mimic that same work that's done for control plane endpoints for all of our application endpoints.
Yep. So how did we implement this? KubeTLS uses Kubernetes' webhook interface. Kubernetes provides a webhook interface either in validating or mutating forms where you can either approve, deny, or you can also optionally make changes to pods or any object really as they're created or modified. KubeTLS is our service that implements this webhook. It watches for, it accepts webhook requests when pods are created, and it modifies them to include the TLS secret with that pod certificate and key.
Exactly. So let's take a demo.
Yeah, cool. Demo time. So we have here a cluster where we have already started up our KubeTLS, but it is not yet running. We're going to look at one of our existing pods.
This info container pod is a diagnostic program that we've deployed, and it just prints out the environment that it's running on the particular cluster. Yeah. But let's look at how, describe it and look at how it's been deployed.
So you'll notice that Kubernetes has already mounted a secret that we didn't put there. This kubernetes.io/service account is from default token, whatever, is a service account token that the pod can use to communicate with the Kubernetes control plane. It's already there, it's mounted. We didn't put that in the pod specification or our deployment specification. Kubernetes added that. And so that's what our Webhook controller will be doing. So let's apply that mutating webhook.
Webhook mutating.
Cool. And we'll take a look at what's actually contained in that definition. So Kubernetes knows that it should connect to a service named KubeTLS in our default namespace. Here is the path that it's calling. Here is the port that it expects the service to be running on. And here is the certificate authority that it uses to verify that webhook. So it expects that that webhook will be running over TLS and will have a certificate signed by, in this case, the Kubernetes cluster authority itself. We've done a little bit of bootstrapping here. So now that we've got that running, now that that webhook is running, we're going to delete our pod.
Well, did we take a look? We did not take a look at that running pod.
Right,
so
let's look at that running pod first.
So let's look at what info container sees in his environment.
Yes.
So we'll port forward and take a look at the output from info container in our browser.
B2. So I add the port in.
Yes.
Cool. So let's look at localhost 80.
Localhost, you misspelled it.
It helps if I spell that right. Yes. Cool. So here is the environment that this pod is running in. It has, a bunch of environment variables that are set. And as you can see that Kubernetes has mounted in /var run secrets kubernetes.io service account. It's got the cluster certificate, the namespace the pod is running in, and a token that can be used to communicate with the Kubernetes API server. So now we'll go back and we will delete that pod. And we'll get our pods. There should be a new one running. Cool. So let's look at this.
WCR9.
Yeah. So now that a new pod has launched with our mutating webhook in place, where did your cursor go? Do you see it?
Yeah, it's right. It was. Okay.
There we go.
There we go.
Okay.
I just moved it on you.
You're going to take the cursor, Dad. Take the cursor.
Okay.
So here is our TLS secret. It is mounted at a well-known location, and that is the result of the mutation that our Webhook controller has done. It's just mounted a secret there. So we'll look at the new containers environment. Cool. And as you can see, there's now a new folder there with our TLS key, our TLS certificate, and the other versions and formats of that. All the information that we need to communicate with other pods securely.
So let's talk a little bit about what those are. So those are the certs, the TLS cert and the TLS key that are needed by Golang. And then here are some PKS12 certificate key stores that are used by Java.
Yeah.
And these are available to the pod. And notice that we are actually running our pod as a non-privileged user. So you can get at these secrets. This is the right way to distribute these secrets, is mounting them as file systems rather than pushing them through the environment. This way that the application can open up those files and read them.
Yeah, cool. It's also worth noting that the Java version contains the same key. It's just formatted differently.
Yes.
Cool. So now that we've shown you what we're doing, let's show you what that request actually looked like.
So when the kubelet creates the pod, it calls the Webhook mutating controller, and it sends this body as the request of what it's doing. So this request says, hey, look, we're asking for an admission review, and here's, we're requesting to be set up for a pod. When we registered the webhook, we said we're really only interested in looking at pod creation. So that's what it's telling us. This request is pod creation, various other information. And then down here at the bottom, the actual pod that's being requested is in this request. So we can take a look at that pod information to figure out how we're going to create the secret for this right here. What we do is on return, we send back the original request that came in, the original body, with the response item down at the bottom. And that response item has this allowed flag that says whether or not we approve this request. We could prevent this pod from being created, but in this case, we want to create it, but what we want to do is we want to patch it. And so in this patch field, we have a base 64 encoded JSON patch. So that's the patch type. What we do there is two separate things. One is we're going to add into this path into the pod's YAML or JSON this particular mount. Then we're going to add a second thing, which is we're going to add on the spec volumes mounting this particular secret. So, and that's what we just saw with info container, is that it had a volume mount for this secret, and inside that secret were those files that has the certificates that were immediately created at that for this particular service that this pod is working on.
Cool.
This is the Golang code that creates that. This is pretty much what we say. The first fiddly bits here are simply getting the pod out of that incoming body, request body. Then we use the namespace and the services that match this particular pod. We get that list, and so now we know that we can generate a certificate for that, a secret that contains a certificate for those endpoints. So we could go create, either look up if we've previously created that certificate and can reuse it, or if we need to create a new one. Then we mutate that request by adding in those JSON patches, and we send that back as the response. This is shortened to Go code. Rest assured, we do take care of looking at the error values and doing the right thing when we get an error. But this has been shortened down so we can show it on one screen. This is in our repository that's freely available. So please feel free to check that out. The repository will be listed at the end. But we said at one point we're going to create the certificate. This is that certificate creation process right here. So we generate up here at the top a key pair. So we create an RSA private key, and we match that with the public key, and we create a X.509 certificate request, and then we embed that X.509 certificate request in a Kubernetes object for a CSR. So those two go to the go to this Kubernetes certificate authority to get signed. So notice that we create this X509 object with the DNS names for the service endpoints, and it's created correctly. And then we ask that this certificate request get signed for these usages. So digital signature, key encipherment, server auth, meaning a server certificate, and client auth, meaning I can go call server, use this, present this to a server as a client and be authenticated. And then after we've created this CSR object in Kubernetes, we then down here at the bottom update and create an approval for that object. So we create the CSR and immediately approve it because we want every pod to have an approved certificate. The way we create that secret then, the last thing we need to do is create the secret that's going to get attached to this pod. And so we just take all of the secret information that's up above. We do some conversions into PKCS12 format for Java applications that can't easily read PEM files. That's not the way. So we simply create convenience files for Java applications. But like Ted said earlier, they contain the exact same cert that we've created and used for Golang. So we've created these certificates and we've given them to both clients and servers, and it happens automatically when the pod is creation. Let's demonstrate how a system might use this for mutual authentication.
Cool. So demo number 2. So this is the Golang gRPC. We have not modified a whole lot of it. So let's look at what the server looks like. So the only thing that we have done to this is, rather than grpc.new server, we call it with Kube TLS service creds, which just uses our library to automatically load those well-known location TLS server certificates. So having done that, let's start up that greeter server.
Apply.
Yes, we're going to apply because I didn't delete this service.
Okay.
Now we're going to look at the greeter client. Sorry. And again, this is just the demo gRPC service. But again, we call it to create a Kube TLS client credentials with that looks up what we're dealing with. So again, we're going to create.
You have an extra equal sign in there.
Thank you. This creates a batch job. So it will create one pod if it succeeds. And that pod did succeed. So let's look at the logs.
So that pod is a batch pod. So rather than running continuously, it runs to an endpoint and ends in a completed state and stays there so that you can examine it, unlike a terminated pod that disappears because it's can be ephemerally replaced without.
And all that did was it ran and it contacted the server and it, did the simple hello world RPC. but it did so using a mutual TLS authenticated connection between our server and our client. Just that simple, you know, the certificates are already there, and so we were able to make use of them.
Almost invisible, and that's the way we want this, is that it's very easy for developers to use this in their code by knowing that the certificates are always available and then using a lightweight shim.
Yeah. So here is the actual code involved. This is our shim. It knows where the Kube TLS secret is. It knows where the secret key is and where the cluster certificate authority cert is. And then it just creates a TLS configuration. It loads in those certificates, and it sets the client CAs, which is a pool that are used for servers to authenticate clients, and the client's root CAs, which is the pool for HTTP or gRPC clients to authenticate web servers. Those are the same pool essentially, though one of them trusts the system cert pool and the other one doesn't. And all of the rest of this is just a very simple shim around the gRPC dial options.
Right. So it creates a TLS config option that's used on both the server and the client side, just in different ways. But it's the same object with the same pieces. So what's not, the magic here is not in the libraries, but in the fact that the certificates are available across your entire infrastructure. They're automatically created. You don't have to go to some central group to go get them.
Yeah.
And you can easily use them in your code because they're at a known location. You know where to find them.
Cool. So we have libraries in Go. We have libraries in Java.
And we'd like to get libraries. We definitely want to get libraries for, say, Node, and ways to use this with, say, Nginx and Python and other languages as well.
Mm-hmm.
So what does this do for you? Well, let's compare this to Service Mesh, which is another way to add secure communications throughout your infrastructure.
So this is a form of Service Mesh, or rather this is one of the components of a Service Mesh. The Kubernetes way, the simple way that connects to Kubernetes. It uses the Kubernetes certificate authority. The other part of this is using the Kubernetes endpoints objects to do service discovery. This is a lot simpler because it's all done in libraries in your application, very simple shim libraries in your application, rather than trying to, bolt this on top. Not that that's wrong for applications, but if you're designing an application, design it from the get-go with all of this. Compared to Istio, this has a lot fewer contact edges. Istio adds rate limiting and metrics for connections in the middle, but there are two major contact edges between your client and your mesh, and between your mesh and the opposing server that Istio adds, that are frequently a source of debugging problem. I read advice recently that you should include Wireshark in all of your containers that you're going to use with your Istio service mesh. And I think that advice is crazy. Using Wireshark, having communications that you can read with Wireshark is the exact opposite of Mutual TLS in your service mesh.
Yeah.
You really the whole point is that you shouldn't be able to snoop on conversations between these two ends, that it should only be the applications themselves that are capable of communicating with the other end. And installing Wireshark in your containers is just making attackers' job that much easier.
Yeah, so you're adding in a tool to do a man-in-the-middle attack to your infrastructure that's designed to prevent man-in-the-middle attacks. What are you thinking? So the other thing that this does, that Service Mesh does, and we're not just picking on Istio here, we think it's the model itself, whether you're using Console or Linkerd, just adds a lot of complexity to your environment, and it abstracts too much away from your developers. Your developers should understand the security model and the security threats to their application and deal with them. And they can if they're given the tooling to do that, which is the certificates that they need wherever they need them. The key thing about this is that while that you can use these certificates anywhere throughout your infrastructure, You can have any Kubernetes cluster create these certificates, and they're perfectly viable for all communication that happens on that cluster. The other thing is you can also use these certificates in your personal development environments. So in Minikube and K3S, you can also use them on your personal desktop. So we copy the certificates, get them out of the secret store and copy them into the same location on our personal desktop, var run secrets.
Or we have tooling to create a CA, create locally signed certificates for your internal use on your local machine.
Right. So this is a very convenient way for developers to use certificates and to put them shift left on security via those certificates. So where do we go from here?
We'd like to have more languages supported, and ideally all of this work would move into the kubelet. The kubelet is already doing more or less this flow for itself, but it could do this on every pod creation.
Right. The other thing is that this slightly changes with different versions of Kubernetes. So in 1.19, they've changed the way that this stuff works.
Yeah. 1.19 has promoted, there's now a certificates V1, which is different from the certificates V1 beta 1. It changes the signing profiles that the Kubernetes certificate authority is willing to use. It changes how you go about requesting CSRs. We're going to make those changes, but there's going to be some pain involved in that.
Right. So that's where we wanted to go with this tool. We think this prevents prevents a lot of agony for developers and their SRE teams, and really empowers dev teams to go do what they need to do. So take a look at our code here. The repository is right there, Kube TLS, and our presentation can be found on tcbtech.com. And this is the end of this part of the presentation, but we'll see you over in the question and answer session right now. Join us there. Thank you.